All right, so welcome everyone to, I guess, week 5.5 of our biochem reviews. This is technically the 5th week of reviews, but I'm pushing toward week 6 of the content just so that we can try to catch up. Last week was a bit of a longer session just so I could make sure to get as much of the content done and caught up with as possible. This week we're hopefully down to regular schedule, but I may try to go a little bit quicker in case you have any questions toward the end, so I can save time toward the end for that. I'm just going to jump in. So this unit is, in my mind, where biochem really starts being biochem. So last time we talked about alpha helices and beta sheets, and that's a lot of biology stuff, but this unit is where we really get into the biochemistry. And so we talk about enzymes and we talk about enzyme kinetics. So the first part of this unit, or the first part of this review, is based on the first part, which is just the enzymes, and then we talk about kinetics, which is my personal favorite section. So just jumping into to question 1, what class of enzyme catalyzes the reaction that cleaves disulfide bonds? So the 6, some professors like to add a 7th classification. It's very, like, there are 2 different systems that include, one includes 6, one includes 7. I think 6 is the easier way to learn it, and it's also the more uniform way to learn it, so I tend to go with 6. So I'm just going to jump in to those 6, and we're going to talk about an overview, and then we'll get back to those 2 questions. So the first class of enzyme is Oxido Reductases. Oh, that's a terrible line. Excuse me. And I'm just going to try to zoom us in a little bit more. Okay, there we go. So Oxido Reductases. Oxido Reductases, exactly like their name suggests, oxidation, reduction. So you have A, which is in its reduced state, B in its oxidized state, and they flip. Right. So some of the examples of this are dehydrogenases, oxidases and peroxidases, and the rest. The big one that I want to focus on is dehydrogenases. I'm not sure if you all are aware, but the 3rd and 4th unit of this class are about a couple of the cycles, and one of the biggest ones we learn is glycolysis. And glycolysis involves quite a lot of dehydrogenase reactions. So that's one of the ones that I like to draw attention to, that a dehydrogenation, the transfer of a hydrogen, is a type of oxidoreductase reaction. Second one is a transferase. So transferases are, my underlining is not very good today, I apologize, but transferases, they take some subunit attached to, or like some part of the protein, and they transfer it to a different protein. So this is something like a phosphotransferase, an aminotransferase, a glycosyl transferase, et cetera, et cetera. These are a little bit more common in biochem 2. I believe you see 1 phosphotransferase, if I remember correctly, in biochem 1. But these are, you know, when we learn about post-translational modification, how something can get methylated, how something can get phosphorylated. Phosphorylation is different, I shouldn't say that. But generally speaking, some of these post-translational modifications are done by transferases, okay? The next is hydrolysis. And I want to emphasize really hydrolysis and ligases and lyases. So these 3 can be similar, and one of the big reasons that they're similar is these double arrows, right? A hydrolase tends to cleave a bond using water, okay? However, it can also form a bond and dehydrogenate, or I'm sorry, and hydrate water. So it can also go this way, where a bond is formed and water is released. Great example of this are peptide bonds, right? It's a peptidase. When we form a peptide bond, I'm just going to kind of work over to this side. You have the N terminus, so your central carbon HR1, NH2, COOH, and you have the, sorry, give me 1 second to finish drawing this, and R2. A single hydrogen, I'm not going to draw the entire mechanism, but it's something along those lines, and then it kicks it off, comes back. You kick off an OH minus from here and an H plus from here. That's, or in other words, you kick off water, right? Peptidases, excuse me, here we go. Peptidases are a great example of hydrolysis because of the reverse reaction, or in this case, it's the reverse reaction. This leftward reaction is the synthesis of a polypeptide, a dipeptide, whatever you want to call it. And in this case, it's the reverse reaction. The forward reaction can also work. Liases are different because liases don't have anything external, like in addition to our two things. So it's literally A plus B gives us AB. That's it. This bonds directly to here. Hydrolysis, you're removing or adding H2O in some way to A and B, and that's why they're different. Liases, you don't normally see them called liases, you see them called synthases. Just because I think it's because it's easier. I don't know exactly why they have so many different names, but liases are very often element specific. So as you guys can see on this right side, carbon-carbon liase, carbon-oxygen, carbon-nitrogen, etc. They help bring together specific elements to bond. Okay. The fifth class is isomerases. Oh, I don't know how that popped up. Give me 1 second to erase that. So isomerases are, I think we all generally kind of understand the idea of isomers is two molecules, atoms, whatever molecules, I'll stick to molecules, that have the same chemical formula. So this, I don't know, we'll do something like that. And let me think if this is a good example. It might not be, but oh, actually, that's not what I want to draw. How that popped up, excuse me. So these two, minus and plus, are isomers of one another because they have the exact same elements but arranged differently. And so an isomerase will move some part of a molecule to a different part of that same molecule. Okay, so if it helps to think of them as like an internal transferase, you can, because remember, a transferase will move that highlighted region to a different molecule. This one will move that highlighted region to the same molecule. So if you wanted to think of it as an intramolecular transferase, like it says here on this side, you can. If you want to think of cis-trans isomerases, which you guys talked about in OChem 1 and a little bit in OChem 2, if I remember correctly, you can. Epimerases, you're going to talk about with gluconeogenesis, excuse me, the pentose phosphate pathway in, I think, Unit 3 of this class. So that's coming up, and we can talk about that. Yeah, so those are some examples. And finally, the sixth class of enzyme is ligases. So again, different from liases, ligases or synthetases, excuse me, use energy from typically a nucleotide-based triphosphate, basically. So it brings together A and B, just like a liase would, except it uses the energy of ATP hydrolysis, or GTP, or UTP, or CTP hydrolysis, in order to power the formation of that bond. So exactly like when we talked about liases, they tend to be element specific. So carbon-carbon ligase, carbon-oxygen ligase, and so on. But we also very rarely call them this, right? When we get into glycolysis, when we talk about pathways, and you see synthases and synthetases, admittedly, I don't really think of them as liases and ligases. I think of them as synthase, synthetase. But yeah, so it really is just kind of, so this is just the overview. Yeah, okay. So let's talk about some actual application. What class of enzyme catalyzes the reaction that cleaves disulfide bonds? And this is one that I talked about in the week 4/week 5, I don't know what to call it, the one that we did last week. A disulfide bond is, and I'm just going to put carbons here for convenience and just everything else. Disulfide bonds are, and this is something that is kind of unintuitive to a lot of people, they're redox reactions. The formation of this bond, this disulfide bridge, if you want to call it that, is redox. One of these is losing electrons, one of these gains electrons, and then they eventually release and become neutral. But because of that, the answer to this is actually oxido reductase, C, and not a hydrolase or a ligase like a lot of people might think. And admittedly, I used to think it was a hydrolase or something because it just made more sense than anything else. I was wrong. Okay. What class of enzyme would form a peptide bond? I don't want to take too much time because we did talk about hydrolases and used peptide bonds as an example. It's a hydrolase. Okay. The 6 classes of enzyme, I believe most professors like testing. I've seen questions on exams about them, but not too many. Most of this unit is focused primarily on kinetics. And while we're on the subject of kinetics, this is my favorite formula. I'm always going to tell you if you ask me a question, let's refer to this formula. I'm going to just warn you all now. And when I say let's refer to this formula, I like to split it into the yellow region and the green region. And obviously the colors don't mean anything except for me to reference back to, but basically the first half and the second half. So I'm going to talk about the first half of the reaction, and I'm going to talk about the second half of the reaction, and then we're going to go from there. So the yellow half is basically saying you have some enzyme, okay? And this is how enzyme kinetics works. This is the introduction to it. It'll bind to some substrate, and it'll give you what we call the enzyme substrate complex, or as we just say, ES, right? Once you get to ES, the green reaction comes in, and the green reaction says your enzyme substrate complex will allow the substrate to do whatever it needs to do to turn into this product, and the enzyme is free to react with more substrate, or if it's changed, then something will change, whatever. We're going to talk about that a little bit more next week. But basically, this is the formula we basically base all of this unit on, and so I love using it just because I think it's a great place to start. So number 3, in the above reaction mechanism, why is there no K-2? So if you'll notice, there are double arrows here, single arrow here. And so we have K1 for the rate of the formation of the enzyme substrate complex from the enzyme and the substrate, K-1. So the rate of the degradation, I don't know if degradation is the best word for that, but the rate of the degradation of the enzyme substrate complex into enzyme and substrate. And then we have K2, the rate of the enzyme substrate complex degradation into product and enzyme. We don't have a K-2 here. This is missing. Excuse me. And the reason that it's missing is because it's kind of negligible. And what I mean by that is K2 ends up being significantly greater than K-2. The reverse reaction here doesn't want to take place, right? The point of an enzyme is to lower that activation energy peak on a reaction coordinate diagram. So, sorry, give me 1 sec to draw it out. The point of the enzyme, I'll do this in green, is to bring this way down. And so when it does, it makes this reaction a lot more favorable. And so because this reaction is so favorable, K-2 is, I don't want to say it can be ignored, but it's one of the simplifications that we make that really cleans up this process, because it's so much smaller that we're looking at something like for every 1,000 of K2, or of like this side, 1 of this side will be formed, and that's like at the high end. So this will be closer to like 1 million or 10 million or something when compared to K-2. K-2 is tiny, and so we kind of ignore it in order to simplify our process. Okay. Now, once we've done that, we get what's called 2 assumptions about equilibrium, and they're called the rapid equilibrium and the steady state equilibrium assumptions. Okay, and that's what we're getting into in this next part, as you guys can tell by question 4. I'm just going to go ahead and scroll to it. So real quick, we're just going to talk about each of them a little bit slower. Okay, so rapid equilibrium, and I'm actually going to just do that. So we're going to just slide over here and just talk about rapid equilibrium and steady state equilibrium, and then go back to answer the question. Rapid equilibrium, steady state. Okay, and we're just going to discuss them. So the basic idea behind rapid equilibrium is that the enzyme and the substrate concentrations, excuse me, okay, sorry, my notes are kind of out of order, so I was reading steady state when I was about to start talking about rapid equilibrium. The assumption that we make is that steady state equilibrium is the equilibrium I apologize. This is one of those that's very detail oriented and kind of nitpicky, so I don't want to give you the wrong information. So give me 1 second to make sure my notes aren't incorrect here. Okay. I apologize for the disruption. I have no clue what happened to my PowerPoint or to my note sheet. So I want to pull up the PowerPoint of my note sheet to make sure that I got this right. Okay. So the basic assumption behind rapid equilibrium, there we go, is basically that I'm very sorry for this disruption. Normally my notes are more organized, but I was looking over them to make sure that I had everything kind of combined, and I lost it. Okay, steady state. We're just going to start with steady state to make things easier. So steady state equilibrium is based on the idea that K-1 is comparable to K2. Okay, so let's talk about this with respect to the formula. Oh, excuse me. Okay, there we go. Sorry about that. So what we're looking at here, I'm going to do this in blue, is K-1 and K2. You guys can barely see that, but K2. And the reason that we look at them is because these are the two constants that affect the enzyme substrate complex. Oh, goodness. Okay, we're not going to highlight with that color. Okay, so what I mean by that is once you've formed this enzyme substrate complex, it can either go back to form enzyme and substrate or go forward to form enzyme and product. Those are the only two options it has in front of it right now. So the relative rate constants will help to determine what we see. And that's kind of what steady state and rapid equilibrium are. So when you have one like predominantly over the other, when one is much, much larger than the other is what I meant to say. You get rapid equilibrium. And specifically when K2 is greater, you get rapid equilibrium. When K1 is, K-1 is roughly the same, you get steady state. Okay, so the rapid equilibrium assumption, going back over here, the rapid equilibrium assumption is K2 is significantly greater than K-1. Sorry, I just want to review my notes to make sure that I didn't get this backwards, just to be absolutely certain, because I always have to double check. Yes, okay. So in other words, the rapid equilibrium assumption is basically saying, since we assume that K1 and K2 are, the forward reaction, basically, because K-1 is so small, a rapid equilibrium is basically the formation of the enzyme substrate complex very quickly. Okay? And so Ks, as we call it, is equal to, I just want to make sure I'm okay, yes. Yeah. I just want to make sure that I'm still in the right area and I'm not going too far because I'm going to need this space later. So Ks, capital K for equilibrium, is equal to the rate constant K1, the rate constant K-1 over K1. And the reason that we get that is, remember, the equilibrium is based on the reaction. So we set up K1 times enzyme times substrate is equal to K-1 times ES. And then when we solve for the equilibrium expression of ES over E times S, that ends up giving us K-1 over K1. There we go, yes. And so we're just going to write that K-1 over K1. And this is what's called the steady, oh wait, no, this is the rapid, excuse me. Yes, this is the rapid. We use Ks for just the first half of the reaction. I always just say S for steady state, but that's not correct. And so this describes the dissociation of the enzyme substrate complex. All right, so that's the rapid equilibrium assumption. I want to make sure okay. So then steady state, since they're comparable, we now have to account for, and I'll do this in blue. So since they're comparable, we can't just ignore one or the other, right? We have to account for them both. And so when we account for them both, we get Km, which is known as the Michaelis constant. And we're going to talk a lot more about Km kind of toward the end of this section. Km is equal to sorry, I always flip this. So the Michaelis constant is equal to K1. No. See, this is me flipping it again. K-1 plus K2. That's a -1. -1. I'm just going to redraw that. K-1 plus K2 over K1. So Ks is just the dissociation of the enzyme substrate complex back to enzyme and substrate. Km is, so if we think of K-1 and K2, it's the removal of ES in any way over the formation of ES. So the ones that we highlighted in blue over here, -1 and 2, these are the ways that the enzyme substrate complex is removed. K1 is the way that it's formed. Okay, and so that's kind of what we're getting at there. So there we go. I don't know why it doesn't slide over easily, but okay, so let's actually answer this question finally. So the assumption that rapid equilibrium relies on, or the assumptions, are, first of all, like we said, K2 is significantly greater than K-1. So let's figure out what that means with respect to these two. The breakdown to form product is slower than the breakdown of ES, and this should be the dissociation of ES would be a better way to put it. Dissociation. In other words, K2, because that's the product forming rate law, is slower than the dissociation, so K-1. Well, that doesn't make sense with what we picked for D. So that one's out, and I don't know if I need to say this, but C is also out. Then once again, so the breakdown, forming product. So the breakdown to form product is once again K2, this is K-1, and it's slower. In other words, the answer to this is B. Okay, all right. So now under which equilibrium does Km equal Ks? So the basic assumption that, and I'm just going to work down here. We said Km is equal to K-1 plus K2 over K1, and we said that Ks is equal to K-1 over K1. Did I flip something? I feel like I might have flipped something. So when K2, that's what I did wrong. I wrote Ks wrong. This is K2 over K1, and it's only focused on the formation because we can ignore K-1 because K-1 is so small. That's what I did wrong. And so when we look at K2, So in order for Ks to equal K2, or in order for Ks to equal Km, well, K1s are the same, so the bottom is going to be the same, so the top has to be the same. So K2 plus K negative 1 has to equal K2. K negative 1 has to be 0, or since we're approximating, K negative 1 has to be really, really small. Really small, which, hey, that's the assumption that rapid equilibrium makes. So under rapid equilibrium, Km equals Ks. Okay? All right. So Michaelis-Menten enzymes. So Michaelis-Menten enzymes are enzymes that follow Michaelis-Menten kinetics. I know that's not a very helpful answer, but we're going to talk about what Michaelis-Menten kinetics is from these answer choices. Okay? So I'm just going to read them off, and then we're going to talk about it. So at a low substrate concentration, the enzymes follow first-order kinetics. Okay, interesting. At saturating substrate conditions, the enzyme follows zero-order kinetics. Okay. The enzyme consists of multiple binding sites and catalytic sites, and displays a hyperbolic curve. So those are the four choices we're looking at. So the graph that I'm going to draw is kind of the classic Michaelis-Menten graph. And it's got delta S on the x-axis and V, so rate of like product formation, basically rate of reaction with a Michaelis-Menten enzyme. And the graph looks something like that. It's not bad. Okay, sorry, I have a not so steady hand, so I always worry that it's going to look terrible, but that's pretty accurate. Okay, so let's talk about each of these kind of in order. So first, at a low substrate concentration, the enzymes follow first order kinetics. So I'm just going to draw a dotted line over here. This seems like it's low enough. So what does first order kinetics tell us? It tells us that as we increase S, V increases, right? As we increase the concentration of this thing, the rate will increase about proportionally. And while this graph is kind of curved, it is pretty close to a linear graph. And so A is actually true, which makes it the wrong answer here. Okay? All right, now let's talk about B. At saturating substrate concentration, the enzymes follow for zero-order kinetics. So again, let's remember zero-order kinetics. As we increase the substrate, that has no effect on the velocity. No matter how much we increase the substrate, velocity doesn't change. And admittedly, I kind of cut this graph off early. If I had kept it going, it would look like that. And that's actually exactly what we see, right? As this curve kind of flattens, the rate stops changing no matter how much we change our substrate concentration. And so B is also true, okay? All right, I'm gonna skip C since we can't really get it from this graph, and we're gonna go to D. D says the enzymes display hyperbolic curves. So this curve is hyperbolic. Like that is the name of the curve shape. And so this one is also true, which makes this false. All right, so now we're down to C. And I'm just gonna tell you guys, C is the correct answer because it's incorrect, if that makes sense. Like C is false. And the reason that C is false is because this is just a definition that you have to know. Michaelis-Menten enzymes have one catalytic site. One site. So and this is going to be obviously not a real drawing, but this area right here is the one site that substrates can bind, and it's the one site that forms product. That's it. That's just the definition of a Michaelis-Menten enzyme. Okay. So Michaelis-Menten enzymes give us, or I should say the formula for the Michaelis-Menten equation, I should say, is, I'm just going to clear this space so I can write it, is V0 equals Vmax times S over Km plus S. And I want to take some time to talk about each of these for a moment, and especially Km, because I told you all we would talk about it, and this is the perfect time to. Okay? So first, let's start off with Vmax. Vmax is this kind of upper bound right here, right? This is Vmax because no matter how much I increase my substrate concentration by, I'm not going to get any faster. And this makes sense, right? If I've got 10 enzymes and 1,000 substrates, well, I can only do 10 reactions at once because I just have 10 enzymes, right? So That's Vmax is saturating conditions like it says up here. Okay, every enzyme is in an enzyme substrate complex or is in the process of catalysis or not necessarily catalysis, it's reacting, right? So that's Vmax. Substrate concentration is substrate concentration. Great. Okay, so now Km. Km is, okay, I thought my computer froze for a second because I couldn't see my mouse. I apologize. Okay, so Km is, and I'm just going to redraw this graph, is what we think of as affinity, right? So there's the graph. This is once again S, and this is V. Okay. Oh, actually, before I get into Km, I should explain the two different V's. V0 is V at any point. So what is the velocity when the concentration is here? What is the velocity here, or anywhere else along this curve? Okay. Just want to mention that because I didn't explain that well. Km is affinity. So Km affinity. More appropriately, Km is the inverse of affinity. Okay, and here's why. The numerical value for Km that we get is, or the definition, if you want to think of it as the definition, is if Vmax is right here, we go to 1/2 Vmax, which is somewhere around right here. So 1/2 Vmax, draw that dotted line, goes to here. This is Km. So Km equals concentration at which V equals 1/2 Vmax. Okay, that's like the formal definition. So let's talk about this in terms of affinity like I've been saying. So if there's a high Km, so if Km is somewhere over here, actually I should do this in different colors so that we can tell them apart. So Km is here. And obviously this graph is not built for this, so we're just going to pretend it works. But so this would be Km. If Km were, and I'm just going to do one more in blue, here. Right? We can trace it up, whatever. Okay. What the red one is telling us is that you need, let's throw some units in here. 1, 2, 3, 4, 5, somewhere like 5 molar of substrate to get 1/2 Vmax, right? Whereas if it were blue, oh, and I'm going to put this in the red box so that we know that we're talking about the red one. I apologize, I should have written that in red. If we're talking about the blue one, you need like 1.5 molar of substrate to get 1/2 of Vmax. So what this is telling us is, if we think about this kind of in terms of what's happening. So if I just have a beaker or a cup or whatever, and I've got enzymes here in green, if I have, if they collide with our substrates at a rate proportional to their concentration, then what this is saying is that this red one needs a lot more collisions, or like interactions, wouldn't be a better way to say this, interactions between E and S to get ES, right? And so that's why we say Km is a measure of affinity, and specifically it's the inverse of affinity. So, okay, there we go. The lower the Km, the higher the affinity of the substrate for the enzyme, or vice versa. So of the enzyme for the substrate. For the substrate. Okay, this is Km. So if I were to give you two numbers and I were to say Km equals 12 and Km equals 4, whatever the situation we're dealing with, this one has a higher affinity for its substrate than the 12 one, okay? I hope that makes sense. If it doesn't, please feel free to ask questions. While you do that, I'm going to zoom out so we can start on the next few questions. Okay. All right. Okay. So, a newly discovered enzyme was found to follow Michaelis-Menten kinetics. Cool. So here are our equilibrium constants. And by equilibrium constants, I really should say rate constants. So these are K1, K-1, and K2. And yes, K2 is also known as the turnover number. We're going to talk about that in a little bit. Okay. At what S, or substrate concentration, will initial velocity, so V0, equal 1/2 Vmax? So I'm going to explain the rationale using the Michaelis-Menten equation, just in case you forget, or like you get like 1/3 Vmax or something like that. And then I'm going to talk to you guys about Km in terms of its definition. So if we think back, V0 equals Vmax times S over Km plus S. And now we're defining initial velocity as 1/2 Vmax. 1/2. I'm going to divide Vmax from both sides, and that cancels Vmax entirely. That's out, that's out, that's out, and that's out. And so what I get is substrate concentration over K plus substrate concentration equals 1/2. Okay, we can solve this algebraically by cross-multiplying, etc. What we end up getting is that Km equals substrate concentration. In other words, when your velocity is 1/2 the maximum velocity, the concentration is Km. This is literally the definition of K, of the Michaelis constant, right? The concentration at which V equals 1/2 Vmax. Okay? If you forget it, you can always solve it algebraically, no worries. Okay? But now let's actually calculate it out. Km is equal to, if we think back, K-1 plus K2 over K1, right? It's all the things that get rid of enzyme substrate complex over the thing that forms. Okay, so let's calculate it. We have the numbers. So equals 4.5 times 10 to the 5th, 3.7 times 10 squared, and 6.8, oh no, sorry, 6.5 times 10 to the 8th. Okay, you can plug that into your calculator, and excuse me, you end up getting I think my calculation is wrong. This doesn't make sense. Give me 1 second. You end up getting 0.256. Okay, 0.256. This is the concentration, so molar, at which initial velocity is 1/2 of the maximum velocity. Okay, all right. So now the next question. For the previous Michaelis-Menten enzyme kinetics, which of the following is true? Okay, so I'm just going to knock out the ones that we know are false, and that is D, because we know that it can follow zero order when it gets saturated, and it's C, because if you're following Michaelis-Menten kinetics, you're not dealing with allosteric or like any form of regulation right now. Okay, so all we're left with is steady state, rapid, and E. So if KCAT is the rate limiting step, then that means that it's the slower step. Oh, slow step. And as we can see here, K2, I mean, it is the slow step, sure. Right? No, yeah, this is right. Okay. So K2 is the slow step. So, but we never think of KCAT as the slow step. It's not the rate limiting step. Wait, did I? Oh no, I'm sorry. This should be which of the following are true, and it's select all that apply. Excuse me. Yes, so E is correct because KCAT. Oh, that's what I did wrong. No, that is incorrect. And here's why. KCAT. Am I? this is what okay, I realize now. Back up here, I should have talked more about this. So we're gonna pause this question for a moment because I never explained this fully. So we ignore K-2 in order because it's so small. So we say that K2 is equal to, like I wrote down there, the turnover number. It's also equal to Kcat, which is the catalytic efficiency, the catalytic number, whatever you want to call it. And we say it's equal to. The correct answer is it's about equal to, because technically Kcat would be equal to K2 minus K-2. But as mentioned, we're just ignoring K-2 since it's so small. Okay, I apologize. I should have mentioned that earlier. I got a little bit distracted. Okay, so is it the rate limiting step? The answer to this is kind of. I know that's not a satisfying answer, but it's kind of not. I'm going to mark it as true with an asterisk because it is the slow step, right? K1 is very high, K2 is relatively low. Okay, so all that's left is, does it follow steady state or rapid? Okay, and the way that we can test that is by saying, does Ks equal Km? And if it does, then which assumption is it? Let's scroll back up. If Ks equals Km, we're in rapid equilibrium. That was question 5, excuse me. All right, so I'm not going to actually do this work yeah, I will. Okay, so Ks we said is equal to K-1 over K1. And we're going to plug those numbers in. And I'm sorry, I don't want to write it again. I'm getting a bit lazy, admittedly. You know what I just realized? I did get the wrong number here because I multiplied instead of adding. So if y'all were trying to tell me that and I forgot it, that is completely my mistake. Ignore that number because it's completely incorrect. The real number is that's why my notes felt wrong. 6.93 times 10 to the negative fourth. 6.93 times 10 to the negative fourth. I apologize. So we're going to repeat the same thing, except so we're just going to include K-1 and K1, and we're going to get, so 450,000 over 650 million, or 650, is going to end up giving us 6.92 times 10 to the negative fourth. They're so close to each other that I would be willing to call it the same thing. And so as a result, we know that Ks equals Km, and like we said up here, that is a result of rapid equilibrium. Okay, so this is rapid equilibrium. Okay, question 9 is a very similar question. It's actually the exact same answer choices. But one thing that I want to point out is I'm not going to go through the math for this because I do want to get into the rest of this because I think it gets a bit more fun. Look at the orders of magnitude. That's going to be my number one suggestion. 10 to the third and 10 to the third. K-1 is roughly equal to K2. Up here, we're dealing with 10 to the fifth and 10 to the second. That's a 1,000, like a difference of 1,000. Ignoring the numbers in the front, just looking at that, you know one is significantly greater than the other. Here, you don't know that. Okay. Here, you know that they're about equal, which tells you that you're not going to be able to ignore K2, that this is a steady state equilibrium. Okay, I'm just going to rush through that because that one is really what I want to draw your attention to. Okay, so now there are ways to manipulate the Michaelis-Menten equation and to solve questions using the Michaelis-Menten equation in kind of unconventional ways, and that's what we're going to walk through right now. Okay, so first, for an enzyme following or obeying Michaelis-Menten kinetics, what will be the initial velocity if the substrate concentration equals 3.5 times Km? So I'm going to draw, I'm going to write out the formula one more time. Actually, not one more time. We're going to see it quite a few times. Plus substrate concentration. Okay, so we're looking for initial velocity. And we have, look at our answer choices. It's with respect to Vmax. Awesome. Okay, so now all we need to do is, I'm thinking to myself, let's set Vmax out front, and then we can say V0 equals some number times Vmax. Awesome. And that number is, we're going to solve algebraically. Let me try that again. We're going to solve algebraically to get it with this. Okay, so I'm going to say equals, well, substrate concentration is 3.5 times Km. At the bottom, we have 1 Km plus another 3.5 Km. And all of this is times Vmax, right? Times Vmax, okay? So this bottom bit, you have 1 plus 3.5 to get to 4.5, okay? So 3.5 over 4, oh, I should mention 4.5 Km, and then the K's can cancel. So what this cleans up to is 3.5 over 4.5 times Vmax, which ends up being 7 over 9. The reason that this question is very weird, like none of these answers work, is because this is a weird number. You're not always going to get nice clean numbers. Like most of these are, 3/8, 3/5, 2/5, 1/2. These are nice clean numbers. You don't always get that when you're using Michaelis-Menten. And so I just wanted to draw your attention. This is not an abnormal result. 7 over 9, some weird fraction like that, isn't abnormal. Just make sure you did the algebra right. There's not an easy way to check that, is the real reason that I wanted to point out. Okay, next one. So you're given V0 and S, and you're asked for Vmax, okay? So I'm gonna write out the equation one more time. Actually, I think this is the last time. Oh, no, there is one more in this PowerPoint. Yeah, one more, okay? I think one more, maybe two more, I don't know. Okay, and I'm just gonna plug in the numbers. I know that I'm looking for Vmax in the end, so that's great. Okay, so 50, and I'm gonna deal with the units later. Vmax, 0.5 km over 1 km, and another 0.5 km. So once again, at the bottom, we can just add these to get 1.5 km. You have something times km at the bottom, something times km at the top, or other way around, excuse me. Something times km over something km. You can cancel the k's, and you're left with 50 equals the Vmax times 0.5 over 1.5. So when we multiply over, we get 75 over 0.5 equals Vmax. In other words, we get 150. So the answer to this one is C. There it is. Keep losing my mouse. The answer to this one is C, and that's just a quick, easy manipulation of the equation. I don't think I think you're going to get a fair number of these questions. I just wanted to make sure to go over them because they can be a little bit weird if you're not used to the formula. Okay. So there is this is a figure, I believe, straight from most of your professors' PowerPoints. Some may not use this, but this is where they list Kcat and Km. So Kcat, like we said, is just K2. I'm just going to include it there if it helps. This fraction right here, Kcat over Km, is a special fraction that we talk about. And you're going to see down here, enzymatic efficiency, enzymatic affinity, all of these things. But the one that I'm looking for specifically, the term enzymatic efficiency or catalytic efficiency you may hear, effectively efficiency. This is what we're looking for. This is Kcat over Km. The reason this is such an important number is because there's this concept of a perfect enzyme, okay? And the concept of a perfect enzyme basically says an enzyme is considered, or a substrate, an enzyme is considered perfect for a substrate if its catalytic efficiency is between 10 to the 8th and 10 to the 9th, okay? Let's talk about these numbers. 10 to the 9th is the absolute upper bound. And the reason for that, diffusion. Your molecules simply cannot move that fast because that's above the speed of light, basically, okay? You're never going to have a catalytic efficiency above 10 to the 9th. So if you have a catalytic efficiency at somewhere in the 10 to the 8th range, what that's saying is that this is a really, 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 really efficient process. And so we consider it a perfect enzyme for the substrate because of that efficiency, okay? Just wanted to bring that up. Now let's talk about the questions. So which of the following values is used to report enzymatic efficiency? I just told you, it's D. Okay, right. Which of the following values is used to report enzymatic affinity for a particular substrate? Okay, we talked about affinity before, so I'm just going to give you guys the answer. It's Km, because Km, remember, is the inverse of affinity, but it's a way that we measure affinity. Okay, the enzyme fumarase binds tighter or is more sensitive to which substrate? Okay, so binding tighter, more sensitive, these are words for affinity, right? When I gave you guys that example up here, over to the side, the blue and the red one, right? You need 3 times the concentration of the red one to get to the same binding as the blue one because it binds tighter to the blue. So that's a way that your professors could be asking you, which one has a higher affinity? Same exact thing, right? So let's look at fumarase on this table. It's got Kcat, which we don't really care about. We're looking at Km right now. So fumarase to fumarate has a lower Km. Let's think back. Km is the inverse of affinity, so the lower Km means a higher affinity. In other words, this enzyme binds tighter to fumarate than to malate. Okay, I hope that makes sense. If it doesn't, please ask. Okay. All right, what is the catalytic efficiency of carbonic anhydrase for those 2 substrates, and which is the preferred substrate? Okay, so carbonic anhydrase is right here. For those of y'all who are like, why do I know that? Carbonic acid is, make sure I remember this. It's H2CO3, right? And so HCO3 minus is the conjugate base carbonate of carbonic acid. CO2 is carbon dioxide, obviously. But this is also the buffer system of our blood. CO2 plus H2O gives us this carbonic acid, which can, let me draw this on the side because I don't have space, I apologize. This, by the way, is not something you're being tested on. I just think it's fascinating and, relevant because you are learning biochemistry. H2CO3, and it goes to H plus HCO3 minus. So it's kind of double equilibriums, but the big takeaway is carbonic anhydrase. This is kind of the link to it. So you can either have CO2 or you can have HCO3 minus. Both of them go to the same place. Okay, so now let's actually do the math for them, right? So you're given Kcats and Kms. What I'm going to end up doing is I'm just going to copy these values over so that I can do the math down there. So 1 times 10 to the 6th and 0.012. 1 times 10 to the 6th, 0.012, and these are Kcat and Km, all right? And that one was for CO2, 4 times 10 to the 5th and 0.026. 4 times 10 to the 5th, 0.026. CO2, this was for HCO3 minus, okay? So the catalytic efficiency is 1 times 10 to the 6th over 0.012 for CO2. For HCO3 minus, it's going to be 4 times 10 to the 5th over 0.026, right? And we're gonna calculate that out. The one on the left, so CO2, we get 8.3, excuse me, times 10 to the 7th. Okay. The one on the right, we get, 1.5 times 10 to the, times 10 to the 7th, sorry. 1.5 times 10 to the 7th. Okay. In other words, the catalytic efficiency of carbonic anhydrase is this for CO2. Oh, I should put equals so that it's not a negative sign. And this for HCO3 minus. So the preferred substrate has to be this one, right? Usually we use catalytic efficiency for preferred substrate, but we can also use the fact that this has a higher kcat and a lower km. So this one kind of everything is there, right? For which of its substrates is carbonic anhydrase a perfect enzyme? So remember we talked about that catalytic efficiency number needs to fall between 10 to the 8th and 10 to the 9th. So because these are both 10 to the 7th, the answer to this one is neither. All right. Okay. So this is most of the basic calculation. I don't want to say basic because they're not basic, but the straightforward or the direct calculations that you're going to be doing with Michaelis-Menten equations. What we're about to do next is something that we do for inhibitors. And this is, I think, working ahead a little bit, which I'm hoping is helpful because I personally, this is A, one of my favorite topics just to think about, and B, I think it's really helpful to kind of have a sneak peek at this so that when you watch the lectures, you're a little bit more informed and can pay attention for the things your professor wants you to listen for. So, Lineweaver-Burke plot. This is very similar to the Van't Hoff plot. So we reciprocate both sides. 1 over V, and I'm going to call it V0 so that I don't forget, equals, Km plus S over V max times S. Okay, so now all the manipulation we're doing is going to be on this right side. This is just going to stay put for a while. So when I have x plus 1 over 2, I can split that into x over 2 plus 1 over 2. We're going to do the same thing here. So we're going to say Km over V max times S plus S over V max times S. Okay. On the right side, or like the right fraction, the substrate concentrations cancel. On the left one, we're going to write it a little bit differently. So the overall equation for a Lineweaver-Burke plot that we graph is Km over V max times 1 over S. And I hope you guys can see the similarities with the Van't Hoff plot because it is very similar. Okay, this is the equation for the Lineweaver-Burke plot. Let's talk about the value of this equation. First things first, it's in that y equals mx plus b format. It's going to be linear, great. All right, so we just got rid of that curve and we can actually get real numbers, linear relationship out of this, okay? Your y-intercept b is equal to 1 over v max, right? So 1 over v max is really easy to get, which means you can get to v max easily. Specifically, v max equals 1 over your y-intercept, okay? Your slope is Km over v max, great. Km over V max is the slope. So you could find V max and then use V max to get to Km, or because of this relationship, 1 over negative Km is equal to your x-intercept. In other words, Km is equal to 1 or negative 1 over the x-intercept. So just like that, from looking at the intercepts alone, we can get Km and Vmax. And then from there, that's the entire Michaelis-Menten equation. It's just pick a substrate concentration, you get the formula. Or you get the initial velocity, and you're done. So this is why the Lineweaver-Burke plot is so helpful. It's just a really easy way to manipulate the data so you get a beautiful linear relationship and everything is super smooth. But there's another reason, and that's what you guys see with number 18. Inhibition, okay? So once again, I love this formula. We're going to talk about the formula. So we have about 15 minutes because I did start late. I'm going to do my best to run through each of these three and leave about 5 minutes at the end for questions. So the various types of inhibitors or inhibition are the way that they are because of where they bind / what they do, okay? And here's what I mean. A competitive inhibitor binds only to the enzyme. So plus I. So now rather than get an enzyme substrate complex, we get an enzyme inhibitor complex. Okay. So let's think about this in terms of equilibrium. When you use up your enzyme, so I'm basing all of this on this formula. I just want to make that as clear as I can because I have confused some people before. Okay. effectively, when I introduce inhibitor, I'm reducing the concentration of enzyme. And so when I reduce the concentration of enzyme, Le Chatelier's principle is going to push this reaction to the left. And that makes sense. In some way, you're going to get less product, right? So because it's an inhibitor. Inhibitors are going to give you less product. This is how it does that. By making the formation of enzyme substrate complex less favorable, by messing with concentrations, okay? So let's talk about how that affects Km and how that affects Vmax. So Km first. Km is affinity. What happens to our affinity? Km is going to increase as affinity decreases, right? And the reason affinity decreases is because we've just said we had 50 enzymes bound to substrates, but now some of those are going to go back because we have to remake the equilibrium, and so we're only going to get 40, right? Vmax. And this is one that's a little bit unintuitive to a lot of people. Vmax does not change. And the reason for that is because if I dump enough substrate in there, Vmax will eventually, I'm sorry, not Vmax, the substrate will eventually, what's it called? Will eventually crowd out the inhibitor and get rid of it. And so Vmax will ultimately stay the same, okay? So what I like to do is I like to draw our Lineweaver-Burke plots for the regular, so like if this would be, it's a really good line, I'm happy with that, okay. This is the regular non-inhibited kinetics. Now we're changing Km and not changing Vmax. So let's think about how that affects things based on what we talked about up here. So I'm going to highlight, because these are important in blue, Vmax is equal to 1 over the y-intercept. We've said Vmax isn't changing. In other words, the y-intercept isn't changing. Now we've said Km is -1 over the x-intercept. We know Km is increasing. When Km increases, let's see, the negative sign means this number, so when Km increases, the right side increases. When we undo the negative, that means the right side without the negative, so 1 over x-intercept decreases. In order for that fraction to decrease, wait, I dislike this because it's always very convoluted. I'm going to do it based on this one because I think it's easier. So Km increases. So if we bring the negative out front, if Km increases, this fraction gets smaller and it's negative. Okay? So how does that change the Lineweaver-Burke plot? How it changes the Lineweaver-Burke plot is sorry, there's my red. We keep the same V and our Km shifts. So we get this, okay? So the red is with inhibitor. I just want to make sure that's clear. Now let's think about if that makes sense with the slope too. So the slope is going to be increased just because we know that the Km had to shift inward. Oh, okay, there we go. And the Vmax had to stay the same. So if Vmax didn't change, and I'm looking right here, by the way. Vmax didn't change, Km increased, so the slope increased. So that checks out. Like, that makes sense. We did great there. Okay? So that's competitive inhibition. Uncompetitive inhibition is different. Uncompetitive inhibition, oops, I need a pen, there we go, binds to the enzyme substrate complex. Only the enzyme substrate complex, I should clarify. And it forms the enzyme substrate inhibitor complex. Okay, so again, or not again. So we're not looking at this part now, we're really looking here. Okay, well, we're looking at the whole thing, I should say. And actually, I want to split this into two parts like I did before, the yellow part and the green part, because they're affected differently. So, uncompetitive inhibition, let's talk about it. So first things first, what's happening with respect to Le Chatelier's principle? Looking at the yellow equation. When ES decreases, we have to compensate, so this reaction shifts to the right. In other words, with respect to Km, Km's actually decreasing, because the affinity of enzyme and substrate is increasing to form more enzyme substrate complex to compensate for the complexes that are removed. Affinity increases. Okay. Now what's happening to Vmax? So Vmax is pretty much dependent on this alone, really, right? So we can pour in more and more and more and more substrate. All that's doing is making more enzyme substrate complex, which will ultimately, some of it will go toward the inhibitor, some of it will go toward product. So Vmax also decreases. Okay. I hope that makes sense. If it doesn't, please ask. So I'm once again going to draw this graph, and then in red. So we talked about when Km increases, this line shifts inward. Now Km is decreasing. Oh, oops, hang on. I don't want to undo that. I want to redo that. How do I? Okay, that wasn't right. Okay, I can't find it. I'll just draw a new line. Hopefully it'll look good. Need black for this one. Okay, not bad. Okay, so like I said, when Km increased, the x-intercept moved to the right. When Km decreases, the x-intercept moves to the left. But Vmax is also increasing. Why can't I? There we go. I'm sorry, Vmax is also decreasing. So when Vmax decreases, remember that it's this relationship. So if this decreases, this fraction decreases, which means that the y-intercept is increasing. And actually, and I think this is fascinating, their decrease is like at the same ratio. At the same rate, ratio, whatever you want to call it. So if this gets halved, this also gets halved, right? So what does that tell us? Well, it tells us that the slope, which is Km over Vmax, doesn't change. So, and I'm doing my best to draw these as similarly as I can. You get parallel lines when you have an uncompetitive inhibitor. Okay, I think that's fascinating. I personally love it. I think it's okay. Now our last, there we go. Our last inhibitor, non-competitive. So non-competitive are the weird one, and there are kind of two types of non-competitive inhibitors. There's pure non-competitive, and there's mixed. For the purposes of this class, we're going to ignore the second one. We're only talking about pure non-competitive inhibitors. Okay, and I'm just going to let y'all think for a second. If competitive bind to the enzyme and uncompetitive bind to the substrate, or not the substrate, I'm sorry, to the complex, non-competitive bind to both. This is really fascinating to me how it works. I don't understand it, admittedly. I think it's super cool, but it's so weird. So the reason there's two types of non-competitive inhibitor is because there's actually, in my mind, there's three, but we classify them into. The reason is because a non-competitive inhibitor could bind to the enzyme more than the enzyme and substrate. Or it could bind to the complex more than to just the enzyme. Or it could bind to them equally, right? And so when we talk about pure non-competitive inhibitor has equal affinity for enzyme as enzyme substrate complex. When you have those mixed non-competitive, they have maybe more of an affinity for the enzyme or more of the affinity for the substrate, whatever, or not the substrate, sorry, the complex. It gets really complicated, so we ignore it. Okay, that's like grad level stuff, right? So once again, I'm highlighting that yellow equation. I love this yellow equation, okay? Let's talk about Km. If the inhibitor has an equal affinity for the enzyme and for the substrate, and for the complex, then it's decreasing them at the same rate. They're both decreasing, so Le Chatelier's principle doesn't really compensate either way. In other words, there's no change in affinity, okay? Because they're both being, because the affinity for the inhibitor is equal, or because the affinity of the inhibitor for the enzyme and for the complex is equal, it doesn't pick one over the other preferentially, and so this equilibrium stays about the same And so affinity does not change. However, just like when we dealt with uncompetitive inhibitors up here, when you form that enzyme substrate inhibitor complex, you lose your enzyme substrate complex, and losing that enzyme substrate complex means you're losing the rate at which product is formed, and so Vmax decreases. Okay, so I'm once again going to draw that same. I'm going to draw this a little bit steeper. I think it would look better. Yeah, something like that looks better. Okay, so now let's talk about it. If Km isn't changing, our x-intercept isn't changing. It's here. Okay, our Vmax is decreasing. When Vmax decreased here, we increased our y-intercept. Okay. I apologize. I know it doesn't connect the dots. I'm not the best at drawing these. Okay. So I want to point out, once again, our slope matches, right? Km over Vmax. When this thing decreases, this overall thing increases, the slope increases. That makes sense. Okay. So the reason that I show you these three is twofold. The first is you can be given Lineweaver-Burke plots and asked which of these is the inhibitor, or which inhibitor are we dealing with, just based on these plots. And the only things you'll have to go off of are the slope, the x-intercept, and the y-intercept. And you can tell that now, right? Obviously, it'll take some practice, but this is how we figure it out. Okay. Second, this is a really big topic. Both big in terms of this class and big in terms of biochemistry. This is, in my mind, actual biochemistry. Everything you've done up till now has been memorizing and learning amino acids so that you could learn this. This is where it gets real. And so this is what the actual stuff, like this is what they're focusing on from here on out. Rates, inhibition, regulation, all of these things are going to start becoming relevant, and this is the first part of that. Okay. So I went a little bit over my time. So if we have, I'm going to save these 2 minutes. If anyone has questions, feel free to ask them. If not, thank you all for joining, and I apologize for that delay at the beginning. Okay, thank you. Have a great rest of your day.